To truly grasp the future that's rapidly approaching, we need to move beyond the buzzwords and establish a clear, precise understanding of the core concepts. Let's begin with artificial general intelligence, or AGI. This isn't just a more powerful version of the AI we use today. It represents a fundamental shift in the nature of machine capability, a significant conceptual leap that redefines the boundaries of what technology can achieve. At its heart, AGI is a machine that possesses the ability to understand, learn, and apply its intelligence to solve any intellectual task that a human being can. It's about creating a system with general cognitive capability. Think of it this way. A human can learn to drive a car, then learn a new language, and then learn to cook a complex meal. We transfer knowledge and adapt our learning strategies. AGI is the pursuit of this same adaptability in a machine, a system that can learn new tasks without needing to be completely retrained from scratch by engineers. It's a system that can reason across different domains, from science to art, and transfer knowledge from one problem to another, just as we do. This is the crucial distinction. Unlike current AI systems, which are typically designed for a single specific purpose, what we call narrow AI, an AGI would exhibit broad cognitive flexibility. Today's AI systems are specialists. They are masters of their designated domain, but they operate with blinders on. A chess-playing AI cannot offer you medical advice, and a language translation model cannot pilot a drone. They are powerful, but brittle. Modern AI systems are no longer fully narrow, but they are not yet fully general. AGI sits in that space between the two extremes, defined by its capability to generalize, not just specialize. For example, today's AI can master the incredibly complex game of Go or translate languages with remarkable, near-human skill. An AGI, in contrast, could do both. But it wouldn't stop there. It could also compose a symphony in the style of Bach, then analyze its structure to explain the principles of counterpoint. It could design a more efficient and resilient bridge, and then write the technical documentation for its construction. It could sift through vast data sets of astronomical data to discover a new scientific principle or identify a promising candidate for a life-saving drug. It is the generality of its intelligence that defines it, making it a tool of unprecedented power and scope. And importantly, AGI is defined by capability, not perfection. Humans are not perfect thinkers. We make mistakes. We have biases. We forget things. An AGI does not need to be an omniscient, flawless oracle to qualify. It simply needs to possess a general problem-solving ability on par with a human. This brings us to another critical concept, one that is often discussed in conjunction with AGI and is frequently misunderstood: the technological singularity. The singularity, a term borrowed from physics, refers to a hypothetical future point when technological growth becomes uncontrollable and irreversible, resulting in unforeseeable changes to human civilization. It's a moment where the familiar rules of progress break down and the future becomes profoundly unpredictable, a phase transition for society. In the context of artificial intelligence, the singularity describes the moment an artificial intelligence not only reaches, but surpasses human intellect. This isn't just a quantitative improvement, it's a qualitative one. The creation of a superintelligence could potentially trigger what is known as an intelligence explosion. Here's how that might work. An AGI, being as smart as its human creators, could turn its intelligence toward the problem of AI design itself. A superintelligent AI could rapidly improve its own architecture, optimize its own algorithms, and even design more efficient hardware for itself to run on. This creates a recursive feedback loop. Each new generation of the AI would be smarter and faster, and therefore better at designing the next, even smarter and faster generation. This process of iterative self-improvement could lead to an exponential, runaway increase in its capabilities, happening at a speed that human engineers could no longer keep up with or even comprehend. This is the intelligence explosion, the core idea behind the AI singularity. Understanding both AGI as the catalyst and the singularity as the potential outcome is essential to navigating the profound technological transition we are now entering. When we think of artificial general intelligence, our minds often leap to the dramatic narratives crafted by Hollywood. We picture a singular machine suddenly flickering into consciousness, a digital god born in an instant of self-awareness. This cinematic vision, fueled by science fiction and sensational headlines, paints AGI as a sudden, world-altering event. It's a powerful story, but it fundamentally misrepresents the scientific journey we are actually on. The reality of AGI is far less dramatic, but infinitely more nuanced. The truth is that real research is methodical and incremental. For decades, progress in artificial intelligence was a slow, deliberate march. Scientists built expert systems, explored rule-based logic, and developed early machine learning models. Each step was a hard-won victory, but the ultimate goal seemed perpetually distant. However, the story of AGI is not one of a single breakthrough. It is a story of compounding progress. The slow gains in computing power, data, and algorithms didn't just add up, they multiplied. Like a snowball rolling downhill, the progress started small, but has now gathered immense momentum. The methodical research of the past laid a foundation that is now enabling an exponential acceleration of capabilities. While we have achieved incredibly strong results in narrow domains, from mastering complex games to predicting protein structures, we still do not possess a single, complete blueprint for general intelligence. This is another key departure from the cinematic myth of a lone genius building a superintelligence in a secret lab. In reality, progress is radically distributed. It is the collective output of thousands of independent research teams and open-source communities across the globe. Each group contributes a small piece of the puzzle: a more efficient algorithm, a novel architecture, a better data set. These small, integrated advances feed into one another, creating a virtuous cycle of innovation. AGI is not being built. It is emerging from the combined efforts of a global scientific community. Because of this distributed and incremental process, there is no on switch for consciousness. There will be no single moment when a machine wakes up. The very concept is a misunderstanding of what intelligence is. The goal of AGI research is not to replicate the mystery of consciousness, but to engineer general cognitive capability. Therefore, if and when AGI emerges, it will not be a sudden event but a gradual unfolding. We will see systems become progressively more autonomous, flexible, and capable. First, they assist with complex tasks. Then, they collaborate as creative partners. Over time, those constraints will expand. At some point, we will simply look back and realize that the tools we are working with are no longer narrow, but have become truly general. AGI will be recognized in hindsight, not announced at its inception. Perhaps the most seductive myth is that of the technological savior, an AGI that will automatically solve humanity's most intractable problems: disease, poverty, climate change. While advanced AI is an undeniably powerful tool, it is not a panacea. It is not an oracle that will simply hand us the answers. Many of our hardest problems are not, at their core, technical. They are deeply rooted in the messy, complex systems of human society, problems of social coordination, political will, and ethical disagreement. An AGI could design perfect technology, but that doesn't overcome the human barriers to its deployment. The role of AGI will be to dramatically amplify human intelligence, not replace human agency. Machines can analyze vast data sets, identify hidden patterns, and suggest novel solutions. They can model complex systems and forecast the consequences of our actions with unprecedented accuracy. But the final step, implementation, requires uniquely human qualities: the will to act, the cooperation to build consensus, and the moral judgment to decide what is right, not just what is optimal. AGI will be a partner in problem solving, a powerful collaborator. But the responsibility to make difficult choices and navigate ethical dilemmas will always remain with us. Separating fiction from fact is the crucial first step in preparing for the future that is actually arriving. To truly appreciate the journey toward artificial general intelligence, we must first take a clear-eyed look at where we stand today. The current landscape of AI is a study in contrasts, systems that exhibit superhuman capabilities in one moment and baffling incompetence in the next. This is the era of powerful yet profoundly narrow artificial intelligence. These are not general problem solvers. They are highly specialized tools, meticulously engineered and trained for exceptional performance within specific, well-defined domains. Think of them not as nascent minds, but as the most sophisticated single-purpose instruments ever built. Their power is undeniable, but it is a power that operates within strict, often invisible, boundaries. In the high-stakes field of medical imaging, for instance, AI has become an indispensable partner to clinicians. Trained on millions of scans, these systems can detect patterns indicative of diseases like cancer or diabetic retinopathy, with a level of accuracy that can sometimes surpass even seasoned human experts. They don't understand the biology of the disease, but they recognize the statistical signatures of its presence in pixels with breathtaking precision. This allows doctors to diagnose earlier and more accurately, directly improving patient outcomes. It's a perfect example of narrow AI's strength, augmenting human expertise in a task that relies on pattern recognition at a massive scale. Similarly, the explosion of large language models has transformed our interaction with information. These models can generate astonishingly coherent text, translate between languages with newfound fluency, and even write functional software code. They are masters of syntax, style, and statistical relationships in language. Ask one to write a sonnet in the style of Shakespeare about a silicon chip, and it will oblige. Ask it to summarize a dense scientific paper, and it will produce a concise and readable abstract. This capability feels like understanding, but it's a high-fidelity illusion, constructed from patterns learned across trillions of words of text. And in the closed, rule-based worlds of strategic games like chess and Go, AI has decisively conquered human grandmasters. Systems like AlphaGo didn't just learn from human games. They played against themselves millions of times, discovering strategies and moves that were alien to centuries of human theory. They achieved this not through a superior understanding of the game's philosophy, but through a brute force exploration of the game's mathematical space, guided by powerful search algorithms. They found the optimal path to victory, unburdened by human intuition, tradition, or cognitive biases. The common thread connecting all these achievements is the principle of pattern recognition in vast data sets. Each of these systems is the result of a painstaking training process. They are fed enormous quantities of data, images, text, or game positions, and learn to associate specific inputs with desired outputs. They are not learning a general theory of the world. They are optimizing a mathematical function for a single, specific task. Their impressive performance is a direct reflection of the quality and quantity of their training data and the immense computational power used to process it. But this is also the source of their fundamental limitation. These systems lack any genuine understanding of the world. They operate on correlation, not causation. An AI might learn that roosters crow around sunrise, but it has no concept of the Earth's rotation causing the dawn. It only knows that the two events are statistically linked in its data. This means they are masters of correlation, not causation. They can tell you is likely to happen next based on past events, but they can't explain. This gap is the chasm that separates today's narrow AI from true general intelligence. Consider this: an AI that can label 1,000,000 images of a cat with near-perfect accuracy does not know what a cat is in the way a child does. The child understands that a cat is a living creature, that it is soft, that it purrs when happy, that it might scratch if scared, that it needs food and water. The child has a rich, multisensory, causal model of cat. The AI has a statistical model of pixels. It has learned a label, not a concept. This is the difference between recognition and comprehension. Because they lack this deeper model of the world, these systems can fail in surprising, nonsensical ways when they encounter situations outside their training patterns. Their failures are not like human errors, they are alien and brittle. A self-driving car, expert in millions of miles of road data, might be completely baffled by a stop sign with a creatively placed sticker, misreading it with high confidence. A language model, capable of writing beautiful prose, might confidently state that George Washington was a renowned physicist, simply because it has no grounding in factual reality beyond the text it has processed. These are not just bugs. They are symptoms of a fundamentally different and more limited kind of intelligence. The path from this powerful but brittle state to true AGI requires us to solve some of the deepest challenges in the field. Instilling robust common sense, the intuitive physics and psychology that humans use to navigate the world, remains a monumental task. Building systems capable of true causal reasoning that can plan and adapt in novel situations is the next frontier. And developing architectures with stable long-term memory, intrinsic goals, and a coherent self-model are all active areas of research. These are the missing pieces. So when we see today's AI perform incredible feats, it's crucial to understand what we are witnessing. These are not sparks of consciousness or the dawn of a general-purpose mind. They are the spectacular results of applying unprecedented computational power and vast data sets to narrowly defined problems. Understanding this distinction is key. It allows us to appreciate the power of the tools we have today, while clearly seeing the technical mountains we still need to climb on the path to true artificial general intelligence. The question of when AGI might be developed has no single answer. Within the community, opinions vary widely. Timeline: optimistic, median, skeptical. Some believe AGI could arrive in 10 to 20 years, citing compute growth and breakthroughs in large language models. A mainstream projection places AGI between 2050 and 2100, emphasizing challenges like common sense, causality, and robust goal setting. Others are more skeptical, perhaps a century away, or unachievable with current approaches. The timeline depends on many factors: scientific and mathematical discoveries, economic and social forces, funding for fundamental research, international collaboration or competition, and new computing hardware and regulation. Don't fixate on a year. Prepare for a range of futures, whether in 20 years or in 100. The societal impact: navigating the risks of a post-AGI world. A rapid arrival could cause widespread social and economic disruption. An AGI could automate a vast array of cognitive tasks, writing legal briefs, managing logistics, conducting research. The transition could outpace society's ability to adapt, leading to unemployment and inequality. Power could concentrate among AGI owners, risking social unrest and political instability. Beyond economics, misuse and accidents. AGI could be weaponized: cyber attacks, autonomous weapons, persuasive propaganda. Even without malice, errors in finance, grid management, or diagnosis could be catastrophic. The speed of such systems may outpace human intervention. The deepest risk is the control or alignment problem. Vague goals can yield unforeseen strategies and devastating side effects, like dismantling industry to reverse climate change. These risks demand caution, responsibility, and proactive safety research, not a halt to all AI work. Despite risks, a safe and aligned AGI offers immense benefits. It could read and synthesize all scientific literature, identify hidden patterns and connections, and propose new hypotheses. It could design and simulate experiments at unprecedented speed and scale. This could drive breakthroughs in medicine, materials science, and fundamental physics. AGI could help address climate change, food security, and water scarcity. By modeling complex systems and evaluating interventions, it could optimize energy grids, agriculture, and water technologies. Personalized education could adapt to every learner. In healthcare, AGI could monitor, diagnose early, and recommend personalized treatments. It could relieve tedious and risky jobs, freeing time for creative, social, and fulfilling pursuits. It might improve governance and smooth economies, increasing shared prosperity, if we manage risks well. The goal is not to replace humanity, but to augment it, amplifying human ingenuity and compassion. AGI will transform the global economy and the nature of work. Unlike earlier revolutions, AGI automates cognitive tasks. Routine analysis, information synthesis, and complex decision-making are in scope. White-collar sectors will be impacted: law, finance, administration, software. Some jobs disappear, others shift toward empathy, critical judgment, creativity, and physical interaction. New categories emerge: development, management, and oversight of AI systems. Needed roles include AI ethicists, trainers, safety auditors, and system integrators. Displacement may outpace creation, making transitions difficult. Productivity gains could be enormous. Who benefits? If value accrues to owners alone, inequality could surge, eroding social cohesion. Address with new thinking on ownership models, taxation, and wealth distribution. Invest in retraining and complementary skills, and strengthen safety nets, including options like universal basic income. The central technical challenge is alignment, ensuring AI goals match human values and intentions. Humans speak with unstated context, and AI may interpret literally and unexpectedly. A system maximizing paperclips might convert all available matter, humans included, into paperclips. Values are complex, sometimes contradictory, and culture-dependent. Who decides which to instill? Active research explores value learning, corrigibility, and interpretable systems. No definitive solution yet. Safety must progress alongside capabilities and be built in from the beginning. Organizations focused on AI safety need support to develop trustworthy, beneficial AI. AI safety research is a necessity. When we create AGI, we must do so safely, and we cannot afford to wait. First, researchers and institutions must prioritize transparency and ethics. Foster a safety culture where risks are openly addressed, not dismissed in a race for capability. Collaborate on safety problems, share insights, and develop common testing standards. Engage the public and policymakers with clear, sober explanations of potential and risks. Governments should enable responsible innovation while setting strong, clear guardrails. Increase safety funding and create agencies capable of auditing high-stakes AI. Because AI is global, international agreements are absolutely essential. Decisions must include ethicists, sociologists, economists, legal scholars, artists, and diverse communities. An informed public sustains democratic governance. Artificial general intelligence and the singularity are profoundly transformative ideas. They evoke great hopes and deep fears of losing control. Pop narratives are dramatic. Real AI progress is complex, gradual, and uncertain. Powerful, narrow tools exist now. True human-level AGI remains distant yet plausible. The logical path is balance, cautious preparation, and optimistic ambition. Don't panic or halt research. Pursue benefits for science, medicine, and human well-being. Don't proceed with blind faith. Address economic disruption, misuse, and control challenges. Treat AGI like nuclear energy or genetic engineering. Invest in safety, adopt adaptive regulation, build global norms, broaden the conversation, and educate the public. The future of AI is what we build. Researchers, policymakers, and citizens together. Embrace proactive stewardship to steer toward good outcomes.